Hello, good evening, everyone. Okay, so welcome back after the ENY break, right? So I hope everybody is refreshed and recharged after the break. Okay, yeah. So we have a few more lectures on the MIPS part, all right, and then we'll be able to conclude most likely by the semester break, all right, and then when we come back after the break, we will switch over to the OS part. Okay. Um, so there are two assignments, right, for this module, and one term paper. All right, so the assignments and the term paper I will brief you on next week. Okay, so I think it is quite doable. All right, very similar to whatever you are covering in class. All right, so as long as you spend some time on it, it is something that you can definitely do it. Okay. So that why I didn't want to bring it up earlier yet because we haven't covered enough material. All right. So after this week and next week, most likely we should be there. Okay. So I'll share the contents of the assignments and the term paper. All right. So let me get started with this week's class. Okay. So I hope you all still remember MIPS. Okay. I've not forgotten things that we covered in the last lecture. All right, so in the last lecture, maybe I can just quickly flip through just to recap your memory. So this was the last week, okay, before the break, okay, where we did all the MIPS instructions. So if you remember, we talked about the addressing. All right, then we went on to look at memory access instructions, load word and store word. All right, that is how we read from memory right to memory. All right, then we talked about how C programming, for example, using arrays can be translated to assembly language code. Okay, using this addressing method. Okay, so the main thing was how we can use a base address and an offset. Okay, like basically like what you see over here, a base address and offset, and then a destination register. Okay, so this was, again, all of this is what we did last week. So I'm just trying to quickly refresh your memory. Okay. Okay, so these are just some of the examples that we went through. Okay, so again, assembly language programming is definitely something new to, I think, most of you. Okay, so I mean, maybe some of you have come across it before, but for majority of you, it might be the first time you're looking at it. Okay, and it's a bit different from other type of higher level programming languages because it is not just the logic. Okay, the logical thinking aspect of breaking down a problem into steps is something that you all are very good at. Correct? You already have done computing modules, but the tricky part is always when it comes to assembly language is how do you translate those logical steps into instructions with that map to the hardware you're dealing with. So that part is something that is new, that takes some time, okay, to practice. Okay, so I think the lecture slides are quite good in a sense. They have a good bunch of examples for you to go through all these code again and understand what we're trying to do. So all these were the branch instructions, jump instructions, so the equivalent of if-else statements. All right, so these are things that we went through. Okay, so loops. All right, so how we do loops, again using jump instructions or branch instructions, and inequalities. Okay, less than, greater than, and so on. Okay, so these are all the examples we went through. Okay, so for last lecture, which was 2 weeks back. Okay, so definitely if you have forgotten, it will take a while. All right, but it's fine. Okay, so today's lecture is even though there's a bit of assembly language involved, all right, it is a bit more on the understanding of the instructions themselves. Okay, how we deal with the format of the instructions. All right, so so if you think they've forgotten some of this stuff, don't worry. You can still quite safely follow today's lecture, all right, because it is sort of another part of the MIPS architecture, which is on the instruction format and encoding. Okay, so let me get started with this. So this is the okay. So basically, the overview of the whole idea of machine code is we want to be able to translate higher level code into something that matches the hardware. Okay, in this case, of course, we are focusing on the MIPS assembly language instructions, and of course, there are certain things that we have seen that we do not have a clear explanation yet. Alright, so for example, when I do immediate instructions, alright, or I do a load word, store word, okay, the offset is always limited to 16-bit values. Alright, so there are some sort of limitations, alright, that we sort of see when we look at the instruction. But exactly why those limitations are there, alright, we will understand right now when we look into the instruction set. All right, so what we are looking at in this chapter is understanding how these instructions are actually encoded. All right, so every instruction in MIPS has a fixed length of 32 bits. Okay, so in MIPS architecture, everything is 32 bits. The instructions are 32 bits. The word length is 32 bits. All right, so the data that we deal with, all the internal registers, are 32 bits. All right, so with that, we need to make sure that whatever instructions that we are trying to execute can also be encoded within these 32 bits. Okay, but at the same time, we also want to make the system to be as simple as possible without adding so much of complexity. All right, why? Because when we see the actual MIPS architecture hardware element later on, you will see that by fixing certain parts of the instruction set, we actually can simplify and reuse a lot of the hardware. Okay, so that is the whole idea. We want to keep the hardware as simple as possible and reuse as many blocks as we can. Okay, so in terms of the MIPS instructions, okay, MIPS instructions, we have three basic types of instructions. All right, the three basic types, we have actually seen them already. All right, but the classification are R-type, I-type, and J-type. Okay, so R-type instructions basically have this format. Okay, like what we did the other time, add, for example, S0, S1, and S2. So in R-type instructions, we specify 3 registers, where 2 of them are the source and 1 is the destination. So in this example instruction over here, I will do an add between S1 and S2 and put the result in S0. Okay, so that is what we call R-type. It means it's called a register type instruction. All the 3 parameters you specify are registers. The other type is the I-type instruction. Okay, the I-type instruction is what is also known as the immediate type. Okay, the immediate type, basically we specify 2 registers. One is the source register, okay, and the other is the destination register. And then we also specify 1 immediate value. Okay, so the same instruction add, you can make it an add I instruction. Okay, so it's S0, S1, and maybe 4. So in this case, or this type of instruction, what is happening is I'm specifying 1 register and 1 immediate value. Immediate value basically means like a constant value. Okay, and I want to do a particular operation, in this case add, and then I store the result. All right, so of course it is not just add, subtract, and so on. Even other instructions like the load word, store word, branch are also considered as immediate. Okay, they have the same format. Okay, if you look at the load word instruction, for example, load word, okay, P0, okay, this also specifies 2 registers and 1 immediate value. Okay, so it's also similarly classified as a I-type instruction. All right, of course the activity carried out is different. Okay, why? Because in add I instructions, you're performing a add operation, and you want the result of the addition, which is the final outcome. In the load word instruction, you're also doing an add operation, which is actually this. Okay, you look back at last lecture slides, you can recall that we are doing an addition between the content of register T1 and 4, the immediate value of 4. So we're doing an addition, but this result is not the final answer. It is pointing to some memory location, and we want the data in that memory location to be stored in the destination register. All right, so it is two different types of instructions. Okay, the objective is different, but they are both considered IType. Okay, because you have two registers we specify and one immediate value. Okay, and the last type of instruction is basically called the jump instruction. Okay, so a jump instruction is basically using only one immediate value. So we want to jump to some particular label. Okay, for example, next, and next is somewhere that we assign as a label in the code. All right, so this jump instruction, we haven't actually seen the details of it yet. Okay, we did see it in the last lecture when we talked about the loops. All right, but it's basically an instruction that only specifies one parameter, which is some reference to the address that I want to jump to, or the line that I want to jump to. All right, so these are the three basic types of instructions that MIPS has. All right, so what we're going to be doing is we're going to have a better understanding of how we encode these instructions, all right, in these different formats. All right, and we also must also remember that in the MIPS we have a total of 32 registers. All right, some registers are already preset for certain use cases. So number 0 is 0. All right, and these are the registers used, okay, for some specific purposes. The ones that we generally use for all the coding registers are anything from A0 to T9. All right, so these are general registers that we use. Of course, you can also use V0 and V1. Like I said, when you are writing the assembly language code, you are free to use whatever registers you want. Okay, only in the case where the compiler is doing it, the compiler has its own set of rules to decide which registers that is going to be using. Okay, but when you are writing it, you're free to use. Okay, the question is 0 under R type, I type. Okay, so these are registers. These are not the instruction type. Okay, so if you come back here, the instruction type is how the kind of information that we provide in the instruction. That means, is it only registers, is it immediate value, or so on. So when I specify an instruction, I can specify registers. Okay, either 2 or 3 and so on. All right, so 0 is one of the registers I can use. Okay, the only thing about 0 register is it has a fixed value of 0. All right, so all these are registers, okay, which are within the processor that I can use when I write my assembly language code. The assembly language code itself has 3 types: R type, I type, and J type. Okay, and depending on what you're trying to do, you can use any of these 3 types of instruction to sort of fulfill the requirement. Okay, so let's do a quick poll. Can you all answer this? Okay, if you have not done this before, you just take out your handphone, open up a browser, go to this link, pollev.com/rsnus. Okay, and you should be able to see the poll there. Okay, so the question is basically saying that we have a 32-bit word starting address A000000002. Okay, and it's asking if it is word aligned. Is this address word aligned? Okay, so we did look at this in the last lecture. What is a word aligned address? Okay, and MIPS only works with word aligned access. Okay, all the access is word aligned. I mean, though you have some unaligned word access options, okay, but by default everything is word aligned. All right, so majority of you have said no, okay, which is not word aligned, and that is the correct answer. Okay, so how do we know whether it's word aligned or not? Okay, so the address, okay, so if you look back at the address, it is 0xa0000002. All right, and the easiest way is you need to, if you remember your binary sequence, all right, 0 1 2 3 4 5 6 7 8 and so on. If you just look at the last 4 digits, okay, so 0000001 10 0011 0101 and so on. All right, so when we say it is word aligned, it always has the last 2 bits as 0. Okay, so you just need to look at the last 2 bits of the address, and as long as the last 2 bits are 0, it's aligned to the word. Okay, why? Because one word is 4 bytes. Okay, so that is how you know it is word aligned. So if you look at this example here, this is translated to 0010. That means the last 2 bits are not 0. Okay, so it is not word aligned. All right, so that is basically how you look at the word aligned or not word aligned. Okay. Okay, so there's another question. What is the difference between temporary variable and program variable? Okay, so the temporary variables are generally variables that you can set aside when you create it inside a function. Okay, so for example, if I call a function A, okay, then inside this function A, I create a variable integer x. All right, so this integer x is basically a variable where the scope is only within this function A. Once I finish the function A and I go out, x is no longer valid. All right, so that is a temporary variable, okay, that you can, yeah, that's something you consider as a temporary variable. Okay, program variables, in this case, it could be anything that you declare as, again, it depends on how the compiler sees it, correct? You could classify this as maybe something that uses the, what you call, static variables, all right, or global variables. All right, so again, this is not a fixed rule, right? Again, it depends on how the compiler wants to look at it. All right, these are just some guidelines. All right, of course, these are certain things that are fixed. All right, but and arguments, for example, arguments, what is arguments for? Arguments is used when you pass parameters to a function. Okay, so for example, in function A, you are passing some parameters A, B, C. All right, so these parameters that I pass into a function will be allocated or be passed through using the registers A0 to A3. Okay, so these are all again some guidelines on how the compiler will make its decision on the registers to use. Okay, but of course there are exceptions, right? In that particular situation, if for some reason the registers are not available and it has to use some other means of doing it, it will go ahead and do it. Okay, so okay, this is the first poll. All right, so let's look at another question here just to recap a bit of the thing we covered last class. Okay, so register S0 has this value inside 0x8000, and we are executing this instruction load word P012S0. So what is the memory address that we are accessing? Okay, you answer based on your own understanding. Okay, don't worry about the majority or minority of the poll results. Okay, so you answer based on what you can remember or what you understand so far from what we have covered. Okay, so I think nobody else is responding. Okay, so majority is 0x8012. All right, then we have two other answers, 8000 and 8000 and C. All right, so let's look at this, all right, and see what is happening. So load word. Okay, so the instruction is this: load word T0, 12, and S0. Okay, and we know that the register S0 has a value of 0x8000. Okay, so from this instruction is the load word instruction. So if you remember what we covered, we said that we are taking the content of S0 and we're doing an addition with the value 12. Okay, so the concept is simple. We take 8000 and we're going to add with 12. But this 12 here is written without any prefix. That means by default, the number here is decimal. But my address, I put a 0x in front. 0x in front means what? 0x in front means what format? Is hexadecimal, correct. Okay, so when I want to add two different numbers in different format, I need to make sure they are both converted to the same equal format. Okay, so it's easy to convert 12 to hexadecimal. So 12 is equivalent to 0xc. Okay, so this addition is actually 0x000c. Okay, so the final answer is 800c. So this is going to point to an address in the memory, and that address is 0x800c. And I'm going to take the contents in that address location and put it into my T0 register. All right, so that is what this question is doing. So I think those of you who answered 8012 also have the same understanding. Correct, the concept is correct. Only thing is you thought of just directly adding, okay, because probably you missed out this 0x in front. Okay, so always look at the number format carefully. Okay, if I didn't put the 0x in front, okay, if I just said that this was 8000, okay, if S0 is just at value 8000, then it's correct. Okay, then 8000 plus 12 will be 8012. Okay, but the specific question is specified in hexadecimal 8000. Correct. So the 12 also has been converted to hexadecimal. So that's why the answer you get is 0x800c. Okay, so I hope again the final answer is not important. I think more important is the concept, right? So the load what we are trying to do. Okay, so let's move on. All right, again those two questions are just to sort of kickstart your thinking. Okay, to recap what we have done. Okay, so let's go into looking at the specific format. Okay, for the different type of instructions. All right, so the first one we're going to look at is the R format type of instruction. Now, as we said, every instruction has a fixed size of 32 bits. As a fixed size of 32 bits. Now, what we want to do is we want to use these 32 bits in a way that we can specify all the different type of instructions that we want to do. Okay, and the format that MIPS has chosen is this layout. All right, so this layout is will vary slightly, okay, for the different formats, okay, but when we look at the hardware design data, okay, you will sort of appreciate why we do it in a certain way. All right, so for the R format, this is the layout where we have opcode, RS, RT, RD, shift amount, and function field. All right, so the total is 32 bits. Again, each field has its own name to it. All right, so when the field is 5 bits, you can specify any number from 0 to 31. When the field is 6 bits, you can specify any number from 0 to 63. All right, so this is basically 32 different values. This is 64 different values. All right, and these are the breakdown of how we have allocated all the bits for R format instruction. All right, so let's look at each of these specifically. So what is the opcode? The opcode is the main field that is common to all the different type of instructions. So whether you look at R-type, I-type, J-type, all of them have the same opcode. I mean the same bits allocated for opcode. All right, and the RS, RT, RD are basically the 3 registers that we deal with. Okay, so if you remember, add, for example, you specify 3 registers. Okay, so the 3 registers are specified in RS, RT, and RD. The function field and the shift amount. So this shift amount is only used if it is a shift instruction. If it's not a shift instruction, you don't use this shift amount field at all. Okay, only for shift instructions. So in one of the earlier slides, we looked at the shift left and shift right and so on. So only those instructions make use of this shift field. Now the function field is used together with the opcode, okay, to determine the exact operation that you want to carry out. All right, so opcode and function field sort of work together to tell the processor exactly what is the specific instruction that you want to carry out. Okay, for all R-type instructions, the opcode is 0. So the function field will actually determine the exact operation that you want to carry out. All right, so let's have a look at this and sort of relate it together. All right, so if you look at this instruction, add 8, 9, and 10, we know that the behavior is this, correct? We want the content of register 9 and the content of register 10 to be added together and the result put into register 8. So this becomes your RS, this becomes your RT, and this becomes your RD. Okay, RS, RT, and RD. Okay, so of course, when you look at this, all right, okay, so now when you look at this, you find that why was it be so strange, correct? If I write my instruction in this format, RD, RS, RT, why can't I just follow it the same way? Why don't I just write it as RD, RS, RT over here, and then there is no confusion? All right, I mean that is normal thinking. All right, so there is a reason. All right, there is a reason why the instruction format is in a slightly different sequence. All right, there is a reason for it. Again, many of these things that we are seeing now, the reason for it is something that we will get to appreciate when we look at the hardware design. All right, right now we might still not see the reason for it yet. Okay, but when we look at the hardware design, you actually see why this is so important. All right, so the first register RS is specified here, RT is specified here, and RD is specified here. Okay, and then we have the opcode and then the function field. Now this function field here is 32. Okay, I will show you in a while how we get 32. But right now, basically what you can do is once you get the various numbers in, you can convert them to binary. Okay, so each of this is, so you just have to convert to the equal number of bits. So this is 6 bits, 5 bits, 5 bits, 5 bits, 5 bits, and 6 bits. So you can convert each of them to the equivalent binary value. Okay, so you have a whole binary sequence, and then from there you can convert them to hexadecimal. Okay, so in hexadecimal you group them into bits of 4. Okay, so you split them into groups of 4, and then you get the final answer here. So this instruction, okay, will translate into this binary, this hexadecimal sequence, which is 0, 1, 2, 8, 4, 0, 2, 0. Okay, so this is the actual hexadecimal sequence, all right, or binary translation that the processor will see and execute. Okay, and when he sees this, he will execute this add instruction. Okay, so now you are seeing it at one level lower, correct? Until now, we were just looking at it from the assembly language instruction. Now we are looking at the actual binary representation itself. Okay, so now before we move on, two important things, correct? I mean, one important thing is, how do I know the output value and the function field? Okay, so right now, what I would like you to do is to go to your Luminous. Okay, there is a document there, all right, under files. All right, so if you go down to under lecture, okay, files lecture, there is a document there called MIPS Instruction Set. Okay, MIPS Instruction Set. Okay, if you already downloaded it, you can open it. If not, you can download this now. Okay, and we are going to look at this instruction set to understand how we extract this opcode and function field. Okay, so let me open up my instruction set also. Give me a minute. Okay, so this is the MIPS instruction set. Okay, once you download it, you can open it up. Okay, so this instruction set, of course, is very comprehensive. It has a lot of detailed instructions and information. All right, we don't need to be overwhelmed by it. We just need to look at just a small section of it for our module. All right, so the main part that we need to look at is basically this set of instructions, which is a core instruction set. Okay, the core instruction set. Okay, and from there you can also look at the bottom. We have the basic instruction format, as well as at the right, the register names. All right, so now what we're going to first understand is how to extract all the opcode and function field. So if you look down here under the core instruction set, Okay, so you can see that in this last column here, there is an opcode slash function field. Okay, opcode and function. All right, and for some instructions, okay, then where you see the slash, that means it has both opcode and function. Some instruction there is no function field, so it's only one value. So that one value is the opcode. All right, so if you look at this first instruction add, okay, you will see that the opcode is 0 and function field is hex 20. Now opcode is 0, function field is hex 20. All right, so that is how we get the value. So if you open up a calculator, if you want to convert, okay, hex 20 will be decimal 32. Okay, hex 20 is decimal 32. So that is how we get the values here. So the opcode is 0 and the function field is 32. Okay, so that is how you decode and get opcode value and function field by looking at the instruction set document. All right, so basically what we have seen right now in this first instruction type is, okay, for any instruction, okay, or every instruction in MIPS will get translated into a 32-bit instruction. All right, so that's the first thing. Now, these 32 bits are already sort of pre-allocated to hold different sets of information in different bit locations. All right, and for R-type instruction, this is the particular format. That means it starts with opcode, RS, RT, RD, shift amount, and function. Okay. The RS, RT, RD are the three registers that are already specified in the instruction. Only thing the order is different. Opcode and function field are obtained from the datasheet, I mean the instruction set document. And the last thing that is we have a look at is the shift amount. And like I said, shift amount is only used if it is a shift instruction. So if it is not a shift instruction, then the value is 0. Okay, because you're not doing any shifting. Okay, so that is the R-type instruction. Okay, so let's look at another instruction here, SLL 894. So can you all look at the data sheet and tell me SLL, what is the opcode and what is the function field? Okay, what is the opcode and what is the function field from the data, from the instruction set? I mean, yes, you have the answer on the slides, but try to look at it on the instruction set and tell me what is the opcode and the function field. Okay, so answers I'm getting a 0 and 0. All right, so let's confirm that. Okay, so let's open up the data sheet and shift left logical. Okay, so it's here. Okay, so we can see that the shift left logical is 0 and 0. Okay, so the opcode is 0 and function field is also 0. So it's good. Okay, so all of you answered or you know, but you didn't type, also fine. Okay, so you are able to extract this information from the instruction set. Okay, so once you are able to do that, then the rest becomes quite easy. Okay, because this shift left instruction is again, this is considered a R-type instruction. All right. Okay. Again, this is one of the special R-type instruction that you only specify 2 registers. All right. Usually, all other R-type instructions specify 3 registers, but the shift instructions alone you specify as 2 registers. Okay. And in this case, your RT is this and your RD is this. Okay, so you do not specify any RS. This becomes your RT register and this becomes your RD register. Okay, and this is the shift amount. All right. So whenever you have 3 registers, all right. So this is a thing you must note. Okay, whenever you have 3 registers, this will be your RS and this is your RT and this is your RD. Okay, but when you have only 2 registers, then the first one is the RD, but the second one is RT. Okay, and in this example, the third one is shift. Okay, when we look at other format instructions in a while, we will see that the third value would be the immediate value. Okay, so in this example, your RT is 9, your RD is 8, shift amount is 4, and the opcode and function field are like 0, right? Like what we saw. And since RS is not used, RS is also 0. Okay, and once you have all of this, you just translate into binary, and then from there you can get the actual encoding. Okay, so these are again examples of R-type instructions. Okay, so this is another example. Okay, so I would like you to try it out first on your own. Even though the answer is there, just try it out on your own and try to figure out what is RS, what is RT, what is RD. You can do it yourself and see whether you get similar answers as what you have on your paper there, on your slide. Okay, so I'll give you a few minutes to try it out. Okay, so once you try it out, okay, you will find that it's not so difficult. It's quite straightforward as long as you follow the format. Okay, so the first thing is, okay, to note the register. So this would be your RS, this would be your RT, and this would be your RD. Okay, so once you know RS, RT, RD, you already have 3 fields already filled up. And since this is not a shift instruction, you also know that the shift amount will be 0, okay, because you're not doing any shift. Okay, and the only thing left is the opcode and function field. Okay, and that you can get from your instruction set. Okay, so you can fill up the values here. Okay, so opcode and function field is again from the instruction set. RS, RT, RD is already from the instruction, and the final shift amount is 0 because it's not a shift instruction. Okay, and after that you translate it into the equal binary values. Okay, so the important thing is you must always make sure you translate to the exact number of bits. Okay, so this is 6. Okay, 5, 5, 5, 5, and 6. Okay, so when you convert to binary, you must convert to the correct number of bits that are being used to represent that particular field. Okay, and after that you just group them into groups of 4. Okay, so groups of 4 means, okay, you just pack them together. Okay, so this is 0, this is 2, this is 0, this is 5, this is 5, this is E, this is 0, and this is 0. Okay, so you just group them into bits, 4-bit groups, and then you convert them to the hexadecimal. Okay, so does anybody have any questions, any doubts about the R-type instruction? Okay, so like I said, it's fairly straightforward. Okay, you just need to follow the sequence. Okay, so there's a question: 10, 7, and 5. Is it register number or value in the register? So all these are register numbers. Okay, so if you were to relate this, okay, so for example, add 10, 7, 5. Okay, so add 10, 7, 5. Okay, let me do it here. So how do you relate this? Okay, so add 10, 7, and 5. So what is this 10, 7, and 5 actually? Okay, so this 10, 7, and 5 is actually coming back to your register numbers here. Okay, so let me. Okay, so what is 10? So to know what is 10, you come back here and then you see that 10 is somewhere here, correct? Is in the number 8 to 10. That means 8 is T0, the first register. So 9 is T1, 10 is T2. Okay, so what is 7? 7 is here. So 7 is the last number. So 7 is A3. So 7 is A3. Okay, and what is 5? Okay, 5 is here. That means if 7 is A3, 6 is A2, and 5 is A1. Okay, so the numbers are actually the same as the name of the register. All right, so you can, when you write your assignment language code, of course, we generally use the names because it's easier, but you can also use the number. They are both the same. So this instruction here is equivalent to writing T2, A3, and A1. Okay, so it's the same thing. Whether you use the numbers or you use the names is the same thing. All right, so in these R-type instructions, we are specifying the register. So when I execute this instruction, I'm actually going to the registers, taking the content of those registers, performing the add operation, and putting the result into another register. Okay, so let's move on to the IType instruction. Okay, so the IType instructions is to specify immediate value. Okay, so the immediate value is when you want to do any form of operation, but you want to specify a constant inside the instruction itself. Okay, now if I were to use the same format that I currently have for IType, then what would be the limitation? The only place that I can actually put in some immediate value is inside here. Correct, because everything else is important, correct? I need the opcode, I need the function field, I need RS, RT, RD. Alright, so if I stick to the same RType instruction, then the only space available is this 5 bits of shift amount. Okay, and yes, it can still work, but it is extremely limiting, correct? Because if I only have 5 bits to represent the immediate value, then I can only have numbers from 0 to 31. Okay, so it is not a practical solution, right? Because you want to be able to specify bigger numbers in your instruction. Okay, so how can we go about doing this? All right, so that is where the idea of keeping or reusing whatever you have as much as possible, while we extend and provide some flexibility to grow the architecture. Okay, so that it leads us to this new format or sort of extended format. It's called the IType instruction. So in that, you have opcode, RS, RT, and now an immediate field. And this is specified by 65516. So 6 bits for opcode. So like I said, the 6 bits for opcode is the one true constant. Okay, for every type instruction, you will always have this 6 bits for the opcode. It will always be there. All right, but now you have your RS and RT. Okay, and then immediately after that, you have 16 bits of immediate value. All right, so with this, all right, you can see that there is no RD register. So the RT register is the one that is supposed to receive the result. Okay, so there is always some difference because now we are changing the format a bit to support a different type of instruction. All right, so in the R type instructions, we use always RS plus RT and the result put in the RD register. Okay, so that was the R type instruction. But for I type instruction, there is no so it's not plus in the operation, whatever operation you're carrying out. Okay, put in the RD register. But in the IType, there is no RD. Correct. So the result is actually inside the RT register. Okay, so I'm going to take the RS register, do some operation with the immediate value. Okay, and the result go into the RT register. Okay, so there is a slight change in the format. Now, when I specify 16 bits, okay, so it's up to the power 16 different values, but it is a signed integer. Okay, a signed integer. Okay, so we will look at that when we look at some examples in a while. Okay, so let's look at this instruction over here. Add I 21, 22 minus 50. Okay, so the first thing is we know that this is RS and we know this is RT and this is the immediate. Okay, so for add I, the opcode is 8. Okay, so let's just confirm that, okay, by looking at the instruction set over here. Okay, so under add immediate, okay, you can see that the opcode is 8. So for IType instructions, okay, you can see that there is no function field, it's only opcode. Okay, so there's only opcode which is 8, so that you don't have any space for function field because the lower 16 bits is already used for the immediate value. Okay, and now we have a immediate value of negative 50. Now let's look at how we are going to encode this instruction. All right, so in terms of the field representation, we know that this is how it's going to look like. Okay, the opcode, this is the opcode, the RS, RT, okay, and the immediate. Okay, and this immediate is negative 50. And negative 50, so the rest of it, I think we know how to directly convert. Negative 50, again, we are using the 2's complement. Okay, if you want to get a quick check, you can always use the calculator. Okay, so if decimal, I key in 50 and I put a negative sign in front of it. Okay, so you will see the answer here is this. Let me see if I can make it bigger. Okay, so the last bits. So again, all the ones in front is just depending on how many bit system you use. Alright, so this is a 64-bit system, so it just extends the ones all the way. Okay, so what we want is that the lower few bits that represent the value. So this is again 1100, 1110. Okay, and the upper 8 bits are all ones because it's a negative value. All right, so if you just want to confirm this, again, you can always do the complement, okay, the standard way. Okay, so let's just look at 50. In decimal is in binary is 110010. All right, so it is 00110010. Okay, and if I were to do the 2's complement, okay, if I were to do the 2's complement, it will be 11001101, and I add a 1, so it becomes 0 carry 1. Okay, and then it will be 1 all the way. Okay, and that is the answer you get here also. Okay, 1110, then it's 1100, and the rest is all ones in front. Okay, so it is the 2's complement representation that is the default way of representing negative numbers. Okay, so of course you need to do this all the time. You can just use your calculator to figure out what is the negative equivalent. Okay, so basically the process is the same. Okay, we look at what is RS, RT, what is opcode. We fill in those fields, and the immediate value is what comes here. Correct. The only thing is, if it's a negative number, you must make sure it's a 2's complement number. And after that, it is the same as before. You just group into bits of 4 and so on. Okay, just carry on with that, and then you can convert to your hexadecimal format. Okay, so this is another instruction. Now, in this instruction, okay, load word, the key thing is this is your RS, this is your RT, and this is your immediate. Okay, so can you try to just do this one more question here, and then we can go for a break. Okay, so I'll give you a few minutes. Try to do it on your own. Okay, so even though the answer is there, just attempt it on your own. Okay, once you attempt it, okay, once or two questions, you will find it, you will have more confidence. Okay, on your own. Okay, so let's look at the steps again. So the first thing is opcode. Okay, RSRT. So RSRT we know is 8 and 9. Okay, immediate is 12. The opcode is again 35. How we get 35? Let's just look back at the instruction set again. Okay. Okay, so load word is over here. Okay, it is hex 23. Okay, so hex 23. Hex 23 is decimal 35. Okay, so that is how they got the decimal 35 over there. And after that, basically the rest is just the same. Okay, you convert to binary, and then you group into 4s, and then you get your final answer here. Okay, so I think now is a good time. We can go for a break. Okay, so it's about 7:35. Okay, so we'll take a 15 minutes break. 7:50 will come back here. Okay, we'll come back here 7:50, and then we'll continue with the rest of this instruction format. Okay, and try to understand how it works. All right, so in the meantime, you have any questions, you can put it in the chat. All right, and I will answer them once we come back. Okay, so I'll see you back in 15 minutes time. Okay, thank you. Okay, so let's resume back. Okay, so there's a question, if immediate value is negative, we need to use 2's complement. Yeah. Okay, so basically the MIPS uses 2's complement system. All right, and so any negative number has to use the 2's complement as a representation form. Okay, so right now we are at the IType instructions. Okay, so we saw the load word just now. Now let's look at another type of type instructions, which are the branch instructions. Okay, so when we talk about branch instructions or jump instructions, we are basically looking to change the address of the instruction or the next instruction that we're going to execute. All right, so normally what happens is, okay, so we execute line by line. All right, but whenever we have a branch instruction, branch is equal okay, then we can potentially not go to the next line. Okay, so we may go to the next line, or we may go somewhere else, either before, after or before. All right, so there is a new address that we are going to go to, okay, and it's not in sequence. Similar to jump. Jump also makes us go to another new location, all right, that is not the next line. So this brings us to the understanding of another important register in the processor architecture called the PC, or the program counter. All right, the program counter is basically a special register that keeps track of the address of the next instruction that is supposed to be executed. Okay, so how can we use or encode the branch start instructions, all right, using the I format? Okay, because when we use the I format, we know that the immediate value that we can specify is only 16 bits. All right, but from the earlier slides, okay, we already saw that the memory address itself is 32 bits. Okay, so every address location in memory, okay, so every address location is specified by a 32-bit address. All right, but when I am specifying the immediate value in a IType instruction, I can only provide 16 bits. Okay, so this 16 bits is definitely not enough to translate to a 32-bit address. Right, I cannot just use 16 bits to directly point to any specific 32-bit address. Okay, so how can I still go about using the 16 bits effectively? Okay, so what happens is the branch instruction is what we call a PC relative addressing mode. It's also an IType instruction, but it's called a PC relative. Okay, why PC relative? Because your jump or your branch is with respect to where the current instruction is. Okay, so where do we normally have branch instructions? All right, so these branch instructions are generally found in if-else statements or loops. Okay, so we can just have a quick look back at the last week's lecture. The last lesson. We will just go to the section on the loops and so on. All right, so you can see down here that whenever you have loops, okay, or if-else checking, that's where branch instructions come in. All right, so this is a typical use case of branch and jump instructions. Okay, so with that understanding, all right, we can say that in most cases, all right, the loops are generally small. All right, and if-else statements are generally just a few lines here and there. Okay, which means that the new address that I want to go to is relatively near to where I currently am. Okay, where I currently am. So that means that what you will do is you will specify a target address that is relative to where I currently am. All right, and it basically will take the current PC value and I add it with the 16-bit immediate field to specify the new address location that I want to jump to. All right, so let's look at an example here. Okay, so of course, another thing we must note is since all the instructions are word aligned, okay, we can immediately multiply that number by 4 to go to the correct word aligned address. All right. Of course, when you look at this, it seems a bit maybe a bit confusing. Now let's look at it from the actual implementation. All right, so basically there is only two things that we need to know. All right, the PC +4 is always the address of the next instruction to be executed. All right, so if the branch is not taken, then this PC +4 will be used as the new instruction address. But if the branch is going to be taken, then what I need to do is I need to take the immediate value that I specify, multiply by 4 and add it to the PC +4. All right. How does this work? Okay, let's look at this example. Okay, then I think it's a lot clearer. Now, if I look at this instruction BEQ90N, okay, so let's understand this first. So I want to do a branch. Okay, I want to do a branch if the content of register 9 and the content of register 0 are the same. Okay, I will do a branch if the content of register 0 and content of register 9 are the same. And where will I branch to? I will branch to this label called N, which is over here. Okay. Now, after I fetch this instruction, okay, my PC is fetching this instruction. Okay, the moment this instruction is being executed, I will immediately go to the PC +4, which is the next instruction. So the PC +4 by default is always the next instruction to be executed. Okay. Now, if I am going to take the branch, from this line, okay, how many lines away am I to the N label? So this is 1, 2, and 3. Okay, so from PC +4, I am 3 lines away. I'm 3 lines away to the label which is N. Okay, I'm 3 lines away. So that is basically all the information you need. I just need to know what is the opcode for BEQ. I need to encode 0 and 9, which is the RS and RT. And finally, the immediate value. And this immediate value is based on the number of lines that I'm away from PC +4. Okay, the number of lines I'm away from PC +4. Okay, so that is basically how you need to calculate this. Okay, so RS is 9. Okay, RT is 0. Okay, and we just need to calculate, do the comparison whether they're equal or not, and then the immediate value is the number of lines of offset. Okay, so in this example, like I said, the immediate value is 3. Why? Because this is PC and this is PC +4, and from PC +4 I am 3 lines away to the label called N. Okay, so if I want to encode this, it will look like this. So this is RS, RT, okay, that is obtained from the instruction directly. BEQ is 4. So let's just look at that from the instruction set over here. Okay, so that is here, branch on equal, which is 4. Okay, and the immediate is 3. All right, so it will automatically know that if the branch is supposed to be taken, I will have to branch to 3 lines away. So that is where the label is. Okay, so of course, when we are manually doing this translation, okay, to the actual binary or machine code, we have to do all this calculation, correct? But in the real scenario, the compiler will do everything for us, right? Because the compiler, when you compile your code, again, you will look at where all these labels are in the lines, and then it will automatically know what number to put in when it is doing the encoding. Okay, so that is one example where I am branching to a label that is in next in upcoming lines. Okay, the immediate is 3 again, because like I said, this is your PC. This is your PC plus 4. And from PC plus 4, it is 3 lines. 1, 2, and 3. 3 lines away. Okay, so that is why you put an immediate value of 3. Okay, now let's look at another example where in this example here, all right, the jump instruction I replace with this. All right, so I mean, I'm just doing this so that so this is equivalent to jump loop, because when I say BEQ00 means register 0 is always going to be equal to register 0. All right, and register 0 is always going to be equal to register 0. So this condition is always going to be true. Okay, so that means this branch will always be taken. Okay, so that is why this is equivalent to the earlier instruction, which is jump loop. A jump instruction is not conditional. That means you will jump always. You're not checking for any condition. You always jump. All right, so we're just trying to replace that with the BEQ instruction to show what happens when you jump backwards or when you branch backwards. So in this example, what happened? I will branch to loop. Right? I will always branch to loop. Okay. So when I say branch to loop, okay. So what will happen? Okay. When my PC is here, I'm executing here. I'll go to the next line, PC plus 4. Okay, so from PC plus 4, where is loop? Okay, so this is back 1, back 2, back 3, and back 4. Okay, so always remember this is the branch instruction, and the PC plus 4 is automatic, because whenever you fetch one instruction, you will automatically go to the next line. So from this new line, how many lines away is the label? So the label here is loop. Okay, so since loop is an earlier instructions, I'm going backwards. So it is -1, -2, -3, -4. So I am 4 lines back. Okay, to do this branch instruction. Okay, so the answer is -4. Okay, that's how you get -4 over here. So now -4 is the one that I need to decode, encode inside my instruction. So RS and RT is 0 and 0. BEQ we saw already from the instruction set. And the last one is the label. I mean, the immediate value that maps to the label. So since we know that the immediate value is -4, we need to represent it in 2's complement. Okay, and put it inside. Okay, so everything else will be the same. Okay, so it will be 4, 4, okay, then 0, and then this will be -4. Okay, so that will be the sort of breakdown of the allocation of the bits. All right. Now let's look at, so that is the branch instruction. Okay, so for branch instruction, we also classify them as IType instruction. All right, because they follow a similar format of having an opcode and 2 registers. Okay, and of course, in this case, we are not doing any addition or any particular operation, but we're doing a comparison, and then we are going to branch to a label. Okay, so the immediate field, the 16-bit immediate field, is used to specify the offset. In this case, it is the number of lines. Okay, so of course, maybe some of you may say that, okay, here I only specify 3, but it's supposed to be 3 lines, all right? And from what we know, 3 lines is equivalent to 12 bytes, correct? Because each line is a word, all right? So how does the 3 gets translated to 12 bytes. All right, because if you look here, this all the addresses are word aligned. All right, that means when I say it's 3 lines away, it's actually 12 bytes away. Okay, this translation of the immediate value to the actual number of bytes is actually done in the hardware. All right, so the instruction is only specifying it as number of lines, that means number of instructions. But the translation to the actual number of bytes, okay, which is a multiply by 4, that is done in the hardware, okay, which we will see later. All right, so later when you see that, okay, I just wanted to link it back to this example here. Okay, now the other type of instruction is what we call the J-type instruction. Now, a J-type instruction or jump instruction basically is unconditional. Unconditional because you do not provide any check. You just say jump. Okay, so if I say jump to next, wherever next is, okay, so next can be here, next can be here, can be anywhere. So wherever next is, I will just jump. I'm not checking for anything. All right. Now, ideally, of course, we can jump to anywhere in memory. All right, but the problem is what? Anywhere in memory means I must be able to specify 32 bits. Okay, but I cannot specify 32 bits. Why? Because there is one constant in all instructions. And what is the one constant? The one constant is the 6 bits of the opcode. Okay, you always need these 6 bits because you need to tell the processor what you're trying to do. Okay, so if you do not tell the processor what you're trying to do, then it cannot make sense of any of the bits in the instruction. All right, so this 6 bits is very important. It's like the key starting point from which the processor will be able to take the next step on deciding what to do. All right, so I need 6 bits to specify opcode, which means I will never have 32 bits free to specify an address. So the only number of bits that are free for me to specify an address are 26 bits. Okay, so I have 26 bits left to specify an address. All right. So how can I translate this 26 bits to 32 bits now? All right. So how we do it is we make two sort of assumptions, not assumptions, two sort of shortcut techniques to convert this 26 bits to 32 bits. Okay, so the first thing is we know that the ending address will ending 2 bits will always be 00, okay, because we have to make it word aligned. All right, so the last 2 bits will always be 0. That means automatically 26 plus 2 will get 28. Okay, so I already have 28 bits right now. Okay, because I know that the last 2 bits will always be 0. Now the next thing is I need another 4 bits. And where do I get the 4 bits? I will get the 4 bits from the PC plus 4. Okay, so wherever my PC plus 4 is, whatever address it is holding at the moment, I take the upper 4 bits and use that to complete the 32 bits of my jump address. Okay, so the maximum jump range is 256 megabyte. All right, so is this enough? It is enough for most of the time. All right, so it is sufficient to cater to most programs. All right, of course, there are other ways that the compiler has a way to go around this limitation. Okay, but we will not go into all that. Okay, so for now, we just look at the J-type instruction. So let's have an example. Okay, so let me look at this example here. All right, then we'll go back to the earlier slide. Okay, so right now I want to encode this jump loop instruction here. All right, this is the jump loop instruction. So I want to encode this instruction. So firstly is we know that for jump instruction, there's only two parts to it: the opcode and the address. So what is the opcode? Opcode for jump is 00010 is basically value 2. Okay, so you can go back to the instruction set over here. Okay, so jump is here. Here's the value 2. All right, so that part we know. Now the next part is the address. So the address I want to jump to here. So loop is having an address of 8. All right, so 8, if I were to look at it, my PC value is currently 24. Okay, this is the PC plus 4. Okay, because once I execute this, I will be executing the, sorry, this is the PC value, not PC plus 4, 20. All right, and I want to jump to this address, which is this address 8. Okay, and if I want to jump to this address, I need to specify this is a 32-bit address. All right, and this 32-bit address that I want to jump to, how do I put it inside my instruction? I can only put in 26 bits in my instruction. So how do I cut away the additional bits? So the first thing is I remove the lower 2 bits because I know the lower 2 bits will always be 0. Okay, and then I remove the upper 4 bits because I'm going to take the upper 4 bits from the PC. So this 26 bits is the one that come here to encode my instruction. All right, so what will happen? Okay, what will happen is, okay, so what is happening is when you are encoding the instruction, this address 8 that you want to jump to will be shortened from 32 bits to 26 bits to be put into this jump instruction here. All right, now when the processor executes this jump instruction, what will it do? Okay, it has to know the actual address that it wants to jump to, correct? So that is where we're going to go back to the earlier slide over here. So when it takes any instruction, any jump instruction, when it looks at the upper 6 bits, it knows that it is a jump instruction, correct? And then it looks at the lower 26 bits, all right? And it knows that this is part of the final address that I want to jump to. But I need to have 32 bits, correct? So to get the 32 bits, I will go in the reverse sequence. What is the reverse sequence? I need to first add another 2 zeros at the end. All right, and at the front, I will take the current most significant 4 bits of the PC, which is this, and add it to the 26 bits. So I'll get the full 32 bits. All right, so it's basically it works both ways. All right, that means when I encode the instruction, which is this example, I take a 32-bit address and I shrink it down to 26 bits using a particular set of rules. So when I execute the instruction, okay, I want to convert a 26-bit address to back to 32 bits. I go in the reverse sequence, which is I add back the 2 zeros at the lower end, and I add back the upper 4 bits on the PC plus 4. Okay, so that allows me to encode a 32-bit instruction into an address for the jump format type of instructions. Okay, so that sort of gives us a good overview of the different addressing modes. All right. or the different format. Okay, so so far any questions that anybody has before I review the different addressing modes? Okay, so let me do this summary here. All right, and I think this is quite important summary because it gives us a perspective of what exactly are we or the different type of things that we can actually do. All right, so the first thing is we can have different type of addressing mode. The first one that we saw was register type or R type, where the register itself is specifying the value. When you write the register instruction, you can specify it as numbers. Okay, specify it as numbers. Okay, or you can specify it as registers. Okay, A0, D1, whatever. Okay, you can specify as register names or numbers here, both the same. Okay, so that is one type of instruction. Then we also saw the immediate addressing, which is where you have two registers plus an immediate value you specify. Now, in terms of using this addressing mode, there are different use cases. All right, so if I look at it in terms of load word and store word, in the load word and store word, the lower 16 bits is storing an offset of the address. Okay, the RS register is holding the base address, and the immediate value is the offset. Okay, this is offset. Okay, and this is the base address. So I add them together to point to some memory location to take the data and put it into the RT register. In the branch, equal branch not equal, the format is still the same. It's still IType instruction, the format is the same, but we are taking we are computing the final address based on the current PC value, which is the base address, with the offset. So this offset is the number of lines either going forward or going backward. And that gives us a new address. But in this situation, the final decision is to change my PC, my program counter. Okay, whether I'm going to PC plus 4 or I'm going to go to a new address. Okay, so you can see that it is the same IType instruction, okay, the same sort of format, but yet because the instruction is different, we are doing many different things. Okay, in the jump instruction format, okay, like what we saw, basically we are taking the PC value, okay, part of it together with the 26-bit address and add a 0 to specify a final 32-bit address. Okay, so these are the different type of addressing mode, okay, that MIPS support R, I, and J, okay, which we need to use to have an idea of how we can support the various instructions we have. All right, so these are just some examples, okay, for you to go through, all right, and then sort of have a feel for how these various instructions are. Okay, PC plus 4 is basically the next instruction, because every instruction is forward. Sorry, 4 bytes. Okay, so if your PC, your program counter is pointing to one address, that means it is currently fetching the instruction from these 4 bytes. Okay, but the moment you fetch this instruction, it will automatically increment to PC plus 4. Okay, because by default, the expectation is it will go in sequence. All right, so the PC plus 4 is basically the address of the next instruction that you want to execute. Okay, so that brings us to the end of this chapter. So give me a minute. I think I've already uploaded the next set of slides. Let me just confirm that. Yeah, it's under the week 6 Okay, lecture 7 data part. Alright, so I think I uploaded just today only. So if you have not downloaded it, you can download it now. So please go to week 6 data part. Okay, lecture 7 data part. Okay, and you will start that now. Okay, so maybe I just give you a short 5 minutes break. Okay, now it's 8:25. I give you a short 5 minutes break. 8:30 we will start the next chapter on data part. All right, where we will see how the architecture itself, all right, is being built to support this 3 instruction format that we just saw. Okay, so let's just take a short 5 minutes break. I'll see you back here in 8:30. Okay, so let's get started with the next topic. Okay, on data part. All right, so this lecture and the next one, okay, these 2 slides are quite hardware intensive. All right, in a sense that we are going to look into the actual hardware design of the processor. All right, and from there we will actually start to appreciate why the instruction format was designed as such. Why did we set aside RS to be here, RT to be here, and so on. All right, so everything is sort of linked up together. All right, and you will see it, okay, once we do this in the next topic. All right, so let's look at this data part. All right, and we are going to build up a processor. All right, and understand how it works. So the 2 basic parts of the processor are what we call the data part and the control. The data part is basically the flow of information. Okay, the flow of information as it passes through the different stages of the processor. And since there are many different pathways for data to flow, okay, we need to have this control mechanism, all right, to decide how or which data goes to which area and so on. All right, so that is where the data part and the control comes in. All right, and what we want is, again, we want to make the design as simple as possible by reusing as much of the available blocks as possible. All right, we do not want to unnecessarily have redundancy, okay, by adding more and more hardware where you can use the same one for multiple applications. Okay, so I mean a simple example would be of course now many devices are touchscreen and so on. All right, but if you look at some basic devices like maybe an alarm clock and so on, where you have a few buttons. Okay, in most devices you have just a few buttons, but the same few buttons will be used to do almost everything. Okay, or a simple example is your watch. Correct. You have a few buttons, but within those few buttons you press, you can set the alarm clock, you can change the time, you can change the brightness, you can do a lot of different things. Correct, because the same hardware, but the way you use it is different. Correct. If I press 1 time, this happens. If I press 2 times, something else happens, and so on. All right. So that is the idea over here. We want to keep the hardware as simple as possible, but yet have some variation to support the different set of instructions that you want to be able to execute. Okay, so there are basically these 5 cycles that you go through every time you want to execute an instruction. Okay, so if I take any simple instruction, okay, so add, okay, S0, T1, and A1. Okay, when I fetch this instruction, okay, from memory, so the first step is I want to fetch this instruction. So all our instructions are inside the memory. Okay, and you compile the code and download it, it's downloaded into memory. All right, and your processor will start to execute these instructions. But in order to execute the instructions, it first needs to fetch these instructions from the memory and bring it into the processor. Okay, where does it know where to fetch from? So that is using the PC or the program counter. So the program counter will keep track of the address of which instruction I need to fetch next. All right, so that is always the first step. All right, you have all these instructions in memory, all your code, and I need to execute it. So I need to first fetch these instructions into memory. Once I fetch it into my processor, I then need to figure out what exactly is this instruction all about. So that is the decoding. All right, and actually that is what we saw just now, correct? The opcode, the RS, RT, everything. All right, so when we look at it from that perspective, we know that exactly what it is supposed to do. Correct. So we know the instruction, all right, from the assembly language, plus when we analyze it from the perspective of how the instruction format is like. All right. Now, after I decode the instruction, I need to fetch the operand. So the fetch the operand means I need to fetch the actual data that I need. Okay, so when I look at this instruction here, I say add S0T1A1. The actual data I need is inside T1 register and inside A1 register. Okay, so I need to go and get this data first. So that's what we call the operand fetch. So I need to get this data from T1 and A1 and make it available for me. Then once I get this data, I can perform or I can execute the instruction. So if let's say it's an add instruction, once I get the data, I can do the add. All right, that's the execute stage. And finally, I store the result wherever it's supposed to go to. So in this case, the result goes into the S0 register. Okay, so these are basically the same 5 cycles that your processor will execute infinitely. Okay, as long as your system is up and running, you are always doing this. You're always doing this. All right, it's just a matter of which instruction you're executing. All right, so in terms of MIPS instruction, again, we have different types of instruction. I will not go through this slide. All right, when we go through all the hardware, you can come back to this and you sort of relate to what we're trying to do here. All right, so let me go straight to the building a processor. All right, and then from there, later we will come back to those 2 slides to review what it is talking about. Okay, so now let's look at it step by step. Okay, so the first step is fetching the instruction. So we know that the instructions are stored in memory. All right, and we need to use this register called the PC or the program counter to point to the correct address in memory. All right, and wherever it points to, that is the instruction I'm going to fetch. And at the same time, like I said earlier on, the default assumption is always sequential. So automatically, it will also lead to increment by 4 to get the address of the next instruction. Now, of course, if there's a branch, there is a jump, you need to make changes to it later on, okay, which we will see. Okay, but by default, we assume next. All right, and of course, once we get the instruction in, then we go to the pass on the instruction to the next stage, which is the decode stage. So let's look at how this fetch stage looks like. So in the fetch stage, basically you have a PC that points to the instruction memory. And what I do is I provide this PC address, PC value will point to a particular address. So what is instruction memory? Instruction memory is nothing more than a collection of all the instructions that we have. So at any point of time, PC is pointing to one location, which is a word address. So if I'm pointing to this location, then this is the instruction that is supposed to go out to the decode stage. Okay, so that is what you're seeing here. When whatever address PC is pointing to, that address, that instruction in that address will come out. Okay, but at the same time, I also want to immediately increment by 4 to point to the next instruction that I want to execute. So that is where this adder block comes in. So this is what we call a hardware adder block. Okay, so a hardware adder block, what does it do? It basically does exactly what it's supposed to do without any sort of thinking behind it, because it is hardware driven. Okay, so the moment you put in any value here, x, you will automatically give me x plus 4, because that is the hardware. It is already designed to just do this one thing. Okay, so there is no variation to it. Okay, it's a hardware sort of design. So what happens is, while the PC is fetching the current, while the PC is pointing to an address and the current instruction is being read out, okay, to pass on to the next stage, your program counter already increment by 4 and stand by here. Okay, already increment by 4 and stand by here. Okay, so again, what is memory? A memory is just a storage element. All right, and it can keep all the information for us, and all we need to do is provide it with the address of which address we are interested in looking at, and it will give us the information there. Okay, so something like this, where in each address location there is an instruction. Okay, so the increment by 4 and passing on all happen at the same time. Okay, so I'll show you in a while. Okay, so what is the adder block? So just now I told you the adder block is a hardware driven block. Okay, so basically it provides, you provide in two numbers and it automatically provides you the sum. Okay, so it is a hardware driven block. In this case, it is 32 bits. So it's two 32 bits add together, give you another 32-bit answer here. Okay, so now, so just now the question, what is happening? What is happening first? Is the PC plus 4 happening first? Is the decode stage happening at the same time? All right, so that is where this concept of clocking comes in. Okay, so in order to make sure that everything works correctly, all right, we synchronize everything to a clock. So this concept of clock is always there for any processor-based system. All right, I mean you heard the clocking number every time you buy a computer or you buy a computing device, correct? Usually they always say, okay, this is Intel or AMD running at 2.4 gigahertz or 3.2 gigahertz or something like that. Okay, so of course for computers, we generally, I mean, sales tactic is to emphasize that to give you an idea of how powerful the system might be. Correct. Of course, increasingly smartphones also are starting to advertise how fast their clocks or processor is running at and so on. Okay, but the whole idea of clocking is that any processor needs a clock to keep everything running at a correct sort of rate. Now, what is this? What can this clock do for us? Okay, the clock allows us to make sure that everything in the system is synchronized. All right, so when the clock happens, everything starts from there until the next clock and the next clock and so on. So everything is synchronized to the clock. All right, so that is where the clocking comes in. All right, so when so let me show you the picture here. Yeah, so as you can see, what happens is when the first clock comes in, okay, so when PC value is 100 over here, which is where we are currently, let's say this is the current value, PC is 100, the adder already perform the addition and generate 104, which is on standby over here. All right, but everything is synchronized with the clock. That means even though the 104 value is already available at the input of the program counter, it will not get updated yet. okay, to the output of the program counter. It will still stay there until the clock happens. So when the clock happens, that is the trigger point for everything to cascade down. So what happens? The 104 will get cascaded from the input to the output. So this one will become 104. So when this becomes 104, the 104 comes here, and this will become 108. So the 108 will come here. All right. So this entire clock duration here, one clock duration, is basically the amount of time the processor has to make sure that the entire instruction that was fetched from address 104 is complete. Okay, because the moment the next clock comes, the next instruction will come already. 108 instruction will come. Okay, so this duration between one clock to the next clock is the amount of time that your processor has to complete the instruction. Of course, this is a very basic level I'm telling you, okay? And this is basically what we call a single cycle processor. Okay, which is what we are covering, okay? The more improved architecture to this, okay, is what we call the pipeline architecture. Okay, so we are not covering that in the syllabus. I can share the notes with you all. If you want for your own self-study, you can look at it. Okay, so that is something we cover for the full-time students here, again, because that is a full-fledged module. This one's full-fledged module. In your case, it's only half the module, right? So we are only covering the single cycle processor. But the pipeline processor basically allows us to break up the whole processor into small chunks. Okay, and just focus on executing that one small chunk within the clock. Okay, so the advantage is you can clock it at a much higher rate. All right, whereas in a single cycle, you need to make sure that the frequency is low enough to give it sufficient time to finish everything. All right, but this idea of clock is basically the one that keeps everything in balance. All right, because only when the clock comes in, the old PC value gets updated to the new PC value. All right, and then the new instruction gets fetched out. And even though the PC plus 4 happens, the PC plus 4 is still waiting for the next clock before it gets updated. All right, so that is sort of the magic of how the clock works. All right, so that is the first stage, the fetching of the instruction from the memory, okay, using the program counter. Now the next stage is basically the decode stage. Now what is the decode stage? The decode stage, we want to make sense of this instruction. Okay, when you fetch this instruction here that comes out, this is a 32-bit instruction. So now that this instruction is out, again, into the processor, I now need to make sense of this instruction to know what am I supposed to do. Am I supposed to do an add? Am I supposed to do a load word, branch, whatever? All right, so I need to figure out what I need to do. So that is where the decoding comes in. Okay, so the decoding has a few stages, a few parts to it. All right, so of course we need to read the opcode to understand what type of instruction it is. And at the same time, once we read the opcode, we will also know the other fields, correct? Because if it is an R type instruction, then I have RS, RT, RD plus shift and the function field. If it's an I type instruction, then I have RS and RT plus the immediate value. Okay, so I need to be able to know exactly what I need to do based on the instruction format. All right, so now let's look at it step by step, focusing on the R type first. All right, and then later on we will slowly expand the processor to support I type. All right, now for the R type instruction, Okay, we need to read from 3 registers. Okay, so for example, when I write the instruction add, okay, S0, S1 and S2, I need to specify 2 registers. So I need to read from 2 registers, and after that I need to write to another register. So where are all these registers? These registers are actually inside this thing called a register file. Okay, they are inside this thing called a register file. And basically, you can think of register file as nothing more than a small memory. Okay, so this small memory only has 32 registers. Okay, so it's the same concept as your memory here. Okay, the same memory here. Only thing, the instruction memory is very big because you have so many instructions. All right, but in this case, your register file is just a small memory. Okay, with only 32 registers. Okay, so there's a question here: is register the same as cache? Okay, so the idea of cache is a bit different. All right, the idea of cache is to keep a local copy of your information in the memory. All right, to improve the access time. Registers are already built into the processor with the aim of allowing the processor to execute the instructions. All right, so the main idea of registers is to actually hold the data for us while it is executing instructions. All right, okay, and basically it is because all the instructions, okay, work with data in the registers. Okay, so if you look at all the arithmetic and logical instructions, add, subtract, shift, whatever, all the instructions require the information to be in the register. So the whole idea of register file is to store this information for us while we are processing it. Okay, so this register file is a collection of the 32 registers that we talked about. All right, and what it allows us to do is it allows us to read 2 registers and write 1 register. Okay, so why must it read 2 registers? Because of the R-type instructions, where we are able to read 2 registers. So the 2 registers that we are going to read, we specify, and the data comes out here. Okay, and at the same time, there is also a write register. So this write register is used when we want to update a register with a new value. Okay, so if I look at add instruction, for example, yes, I need to do that. Okay, so I need to do some operation here, and I need to update a register. So I need the register, I need to be able to write back to a register. Okay, but at the same time, if I take a load word instruction, okay, or a store word instruction, okay, or a branch instruction. Okay, these instructions do not require me to update any register. Okay, so for example, a branch instruction here, I just need to know whether the 2 registers are equal or not equal, and then I decide to branch or not to branch. So when I execute a branch instruction, I don't need to update a register. I need to read from the 2 registers, correct? So I need the read functionality. So I need this, I need this. But I don't need to write data. Okay, so in order to make sure that there is a way to decide whether I need to write or don't need to write, there is another So what we call a control signal here, known as register write. So this, think of it as a switch. Okay, so if the switch is active, then you are allowed to write. If the switch is inactive, okay, then you're not allowed to write. Okay, so this is just a way of ensuring that you do not accidentally write to any register that you shouldn't be writing to. Okay, because you're executing some other instruction. Okay, so the register write is basically what you call a control signal. Okay, to decide which register, when you are allowed to write to register and when you're not allowed to do so. Okay, so let's look at this example here. Okay, so the first step is we want to decode this instruction into the binary format. So this one again, we have just covered, I know. So probably once you go through it a few times, you can sort of easily get this. All right, but if you just recall this RS, this RT, and this RD, that's what we have here. So this is 9, this is 10, this is 8. RS, RT, RD, shift amount. So this is add instruction, so shift is 0. So for add instruction, opcode is 0, and function field is this. Okay, this is 32. Okay, so this is basically the encoding of the instruction into the actual bits. So for this RTA instruction, we know that we need to read from two registers, which is register 9 and register 10. Okay, but more than the actual numbers, what we want to know is the bit position. So in this case, we can say that the bit position 25 to 21 is RS, 20 to 16 is RT, and 15 to 11 is RD. So okay, so this again comes back to the instruction format. So we know that each of it is 32 bits. So it's basically from 0 to 31. So the first 6 bit is opcode. Okay, so that is from 31 down to 26. So that is why 25 to 21 is your RS, RT, RD, and so on. Okay, so that is how we get this bit position. All right, so inside the processor, okay, inside the processor, these are what we call hardwired. Okay, so you can think of it as a physical connection, a physical wire. All right, that means once the 32-bit instruction comes out of your instruction memory, okay, these values in this bit position will immediately get connected to the read register 1, read register 2, and write register, okay, of the register file. And what will happen? So in this case, the content of register 9, okay, because what will come here is value 9, what will come here is value 10. Okay, so the read register 1 is 9 means I'm interested to read the content of register 9. So that would what will come out over here. When register 10 is specified as read register 2, then I'm saying that I want to read the content of register 10. So that will come out over here. Okay, so I'm reading the content of both register 9 and register 10 and making it available at the output of the register file. All right, so of course there is also a write register, which is the register 8. Okay, but we must understand that the data that you want to write is not available yet, because the data that you want to write is the answer, and the answer is only available after the addition is done. Right now, we are still in the beginning stage, correct? We are still only collecting the data from register 9 and register 10. All right. So that is the decode stage. Okay, so let's look at as another example here. So add I 21, 22, 50. Now, this is now a different format instruction. This is IType instruction. Now, for this IType instruction, okay, so the decoding, okay, as what we saw, we have opcode, RS, RT, and immediate value. So this is 21, 22, and negative 50. Okay. Now, if I were to stick to the same, just now I mentioned that this has to be hardwired, correct? That means I'm here, all this is connected, okay, through wires, okay, directly connected. Now, if I stick to the same hardwired connection, all right, and I try to execute this instruction, which is IType, all right, then what happens? Does it make sense? Okay, it doesn't make sense because your RS register is still fine. Okay. So your RS here, so this is RS is 22, this is 21. This is 22, this is 21. Okay, so this is your RS register here, this is your RT, this is your immediate. All right, so your RS register is still fine because you want to read from register 22. Okay, you want to read from register 22. But are you reading from register 21? No. Okay, because in this instruction here, we are supposed to take the content of register 22, okay, do an addition with minus 50 and put the data into register 21. That means this is actually your destination register where you want the result to be stored. Correct. That means this RT, okay, instead of coming here, okay, I should break this and I should come here. Okay, I should connect it to the right register because that is what this instruction wants me to do. I want to take the result and I want to store it into my register 2021. So the 21 register 21 should be specified as the right register. Okay, so you can see that this is a problem. Okay, that means I cannot just take the hardwired concept and just stick with it and expect it to work for all the format. Okay, it works for the R format alone, but once I come to the I format, I already need to make some changes. All right, and this 15 to 11 again doesn't make sense in this context because 15 to 11 is not a register, because in IType 15 down to 0 is the full immediate value. So 15 to 11 just by itself doesn't make sense. Okay, it's 15 to 0 is the data that I'm supposed to use. Okay, so this also doesn't make sense. Okay, so we need to make some changes to the current design to now support the IType instruction. All right, so this is the issue now. So how can I go about solving this? Okay, how can I go about solving this issue here? All right, so what I need to do is the first one, RS, no problem. I can still stick with it. All right, the way to go about solving this is to use this component called a multiplexer. Okay, so what is a multiplexer? Okay, so let me just quickly go through this. A multiplexer, very simply put, is just like how you operate your TV. Okay, your TV is basically one screen, so you can think of the output as your basic screen. But input, what do you have? You have your Netflix. Okay, you have your Disney Plus. Okay, you have everything. Okay, Amazon Prime, everything. Okay, and what do? You switch. Okay, at any point of time you can switch between what you want to watch, but whatever you want to watch you can still only watch on one screen. Okay, but you can have multiple inputs and then you switch using some control. Okay, so the same concept over here. Okay, I can have multiple inputs, but only one of them will get activated to go out. All right, so that same concept now applies here. So this multiplexer over here, okay, what will it do? It will now be used to connect both the RT and the 15 to 11. Okay, so if it was a R-type instruction, then this should go through. All right, because of our R-type instruction, okay, let me just go back here and show you again. Okay, for R-type instruction, 15 to 11 is actually specifying the right register. Okay, so that is what I want. Okay, so for R-type instruction, 15 to 11 is specifying the right register. Okay, but for I-type instruction, the 20 to 16, this is your RT register. Okay, so that is the one that is actually the right register in this case. Okay, so that is the one I want to go through to be the right register. So I need to be able to make a decision, and that decision is using this control signal called register destination. So am I going to select the RT bits, which is 20 to 16, okay, or I'm going to select the RD bits, which is the 15 to 11. Okay, so that is where the multiplexer comes in. It allows us to now have a slight variation in the design, okay, to now support both R-type and I-type at the same time. Okay, so this is what I mentioned just now, earlier, where we said that we want to keep the design as simple as possible, all right, and make changes along the way to support the different things that we want. Okay, because I mean, you might think that, okay, why don't I just create one architecture for R-type, one architecture for I-type, you know, and just put everything together in a big processor. Okay, technically it will work, all right, but again, there is just so much of redundancy, there is a waste of hardware and the cost involved. All right, so since you know the majority of the things are the same, we reuse all of them. All right, and then we just focus on one or a few things that we need to tweak to support the different type of instructions. Okay, so the multiplexer is what I went through. Now the next part is the decode stage. All right, so for the R-type instruction, okay, let's come back here again. Okay, so when I look at the R-type instruction, with this add instruction, I supposed to take this content 9, content 10, add together and put into register 8. That means this data and this data are supposed to go to the next stage and do the addition. Okay, so I can directly take from the two outputs of the register file. But once I come to this IType instruction, what happens? One of it is register, but one of it is the immediate value, okay, which is this. All right, so I need to be able to make a selection on who goes to the next stage to do the addition, because I'm still doing the same addition here. The add is the same. Add and add I, the addition is the same. Only difference is in add, I'm adding between I'm adding the content of 2 registers. In add I, it is 1 register and 1 immediate value. All right, so that's the only difference. So I now need to be able to specify that, and that is by using another multiplexer here. So this other multiplexer here, what does it do? It can now select between 2 different possible inputs. Okay, one is the second data from the register file, or the other option is the immediate value. Okay, and the immediate value is a 16-bit value. What the hardware will do is it will assign extend to 32-bit. Okay, why 32-bit? Because everything within the processor, all the arithmetic and logical operations have to be 32 bits. Okay, so you will have a hardware block to do the sign extension so that the 16 bits becomes 32 bits. All right, and with that, you now have another multiplexer to decide who goes to the next stage. All right, so if this was an R-type instruction, the data from the register file will go through. If this was an I-type instruction, the data from the immediate value will go through. All right. How about load word instruction? Now, load word instruction, what are we doing? We are taking the RS, add with the immediate value, and putting it into RT register. So this load word instruction is also supported with the current design that we have. Because this will be RS, so this will be the content of RS. Okay, the data inside RS. The immediate value here will get extended and come here. So this will be the -50. All right, and both I can do the addition later on. All right, so the load word instruction is supported with the current hardware itself. Okay, don't need any modification. How about BEQ? A branch equal instruction. So a branch equal instructions, I will have to specify, I calculate the branch outcome. Okay, and the target at the same time. What is the branch outcome? Whether this and this are the same. Okay, whether they are the same, that is 1. Okay, so this is the first thing, whether they are the same. The next thing is the line. So I need to do both these 2 things at the same time. All right, so you can see that, okay, current stage right now, the decode stage, this is where we are. Okay, so we have a 32-bit instruction that we have fetched from memory. From the 32-bit, we know that the upper 6 bits is opcode. So we don't worry about that for now. In the next chapter on the, when we do control, we look at that. But for now, upper 6 bits is opcode, we don't touch that. Now the remaining 3 5-bit blocks are the 25 to 21, 20 to 16, and 15 to 11. Okay, if it was R-type instruction, it would be RS, RT, and RD. All right. If it is I-type instruction, it will be RS, RT, and the immediate. Okay, and which register I supposed to write to, again, depends on whether it is R-type or I-type. If it's R-type, it will be here. If it's I-type, it will be here. All right, and similarly, the data that I read out from the register file, the first one is always from the RS. The second one, it could be the data from the RT or could be the immediate value. Okay, to be the second operand. All right, so you can see that we are now slowly building out the processor stage by stage. Okay, and at each stage, we also want to make sure that it supports the different type of instruction that we have. It must support R-type, it must support I-type, it must support J-type. All right, so we are not covering J-type in this syllabus. All right, but as long as we cover R-type and I-type, then we say that it is fine, it works. All right, so I will stop here for today. All right, so I know it is quite can be quite overwhelming. All right, especially when you look at all the things that we are discussing. All right, so I want you to take some time to absorb this first. Okay, so we are not done with this chapter yet. Okay, we are only in the decode stage. We still have the execute, operand fetch. We still have operand fetch, execute, and write back. Okay, to complete the whole processor. Okay, but we need to understand what is happening here, how the data is flowing from one stage to the next stage. All right, and how the processor is actually making everything work in sort of a magical way. All right, so we will stop here for today, and before the next week's lesson, I would like you to sort of just go through this again. Okay, just to understand what is happening. Okay, where are we? Okay, how the data is coming from the memory, how we are decoding it, and so on. All right, so once you understand this, when we go on to the next step on the operand fetch, the execute, it will be a lot easier. Okay, if you look at the slides already, you can see that we are building up the processor until everything comes together. Okay, so you need to really understand at each stage what is happening. Then only when we put everything together, you can sort of see how it flows. Okay, so yeah, we will stop here for today. So thank you very much. If you have questions, you can still ask me. If not, I will see you all next week. Okay, to finish up this chapter. Bye.